In this screencast, I want to look at some of the statistics involving one quantitative variable. So we're going to start with this question. Here's a histogram showing the salaries of 400 employees at a fictional company, and the salaries are in thousands of dollars. Our goal is to estimate the mean. So just to be sure we're reading the histogram correctly, notice this bar here, for example. It goes from 55 to 60. Its height is about 22. This is telling us that about 22 employees are making between $55,000 and $60,000, and we want to estimate the mean. Now, why don't you pause the screencast and estimate the mean before going on, and do that for all the questions in this screencast. Pause and try to answer them on your own, even if you're not sure what to do before moving on. That's the way to get the most out of it. Anyway, I would say the mean is about 80,000. It's symmetric, goes up, comes down, the middle's in here somewhere. Maybe 75 would look okay. I don't know, 85 seems a little high. I just don't think that this represents half the employees, and it is symmetric. If it was skewed, it'd be a little harder to estimate the mean, but I say it's around in the middle here at 80,000. You got something a little different, that's fine. What if we want to estimate the third quartile instead? Well, the third quartile is the top 25%. How much money do you have to make to be in the top 25% of the top 1/4 of the employees? How much money to be in the top 25%? Pause the video. But to do this, first of all, remember that there's 400 employees here. So 25% of 400 is 100. Where are the top 100 employees? So I estimated the heights of each of these bars, 7, 13, 20, 27. That's 42. And I added 7 and 13 is 20, plus 20 more is 40, plus 27 is 67. So 67 employees make more than 95,000 a year. Now this 42 takes us all the way up to 109 employees. Well, I don't want to know 109, I want to know 100. So this bar has 9 employees more than I would like. So if I move in here, if I say, okay, the 25 third quartile is going to be between 90 and 95, and probably closer to the 90 end because I need 33 out of these 42 employees to make 100. So I'm going to guess it's around 91, maybe 92,000, somewhere in there, low 90s. 90 would be defensible, maybe, I don't know, 90 is a little too low, 95 is definitely too high. So I would say 91 is a good estimate, and I would accept numbers that are pretty close to that. Hopefully that's what you got. How about estimating the standard deviation? Now, if you don't know how to do this, then it's really, really hard. But there's a trick that works especially well for symmetric histograms, and it's a good rule of thumb even for non-symmetric ones. And the rule of thumb is you take the largest, subtract the smallest, in other words, you figure out how wide a range it is and divide that by 6. So if we do that here, we would get an estimate of 12.5 or 12,500. 115 minus 40 divided by 6, 12.5, 12,500. And in fact, when we look at the actual data, we estimated a mean of 80. It's 80,688 is the actual mean, pretty close. We estimated a standard deviation of 12,500. Actual standard deviation is 15,000. Pretty darn close. Pretty darn close on this scale. It's really hard to estimate standard deviations. And we estimated a third quartile of 91 or 92, and there it is, 91.4. So the histogram can tell us a lot, and we can do a lot of estimating based on histograms, even if we don't have the summary data. An important idea for us is going to be z-scores. So on a test, the mean score was 300 and the standard deviation was 20. And we've got these 4 questions. If you scored 330, what was your z-score? Let's just take them one at a time. So if you scored 330, what was your z-score? Pause the video. And the thing to remember here is that the z-score tells you how far above or below the mean you are measured in standard deviations. How many standard deviations above or below the mean are you? So the formula for the z-score is you take your particular x, subtract the mean, divide by the standard deviation, and we see the calculation here. 330 minus 300 over 20 equals 1.5. So a score of 330 is 1.5 standard deviations above the mean. So if that makes sense to you, the next ones will all be easy. What if you scored 295? What was your z-score? Well, just do the calculation again. 295 minus 300 over 20 equals negative 0.25, meaning that you are negative 0.25 standard deviations, or 1/4 of a standard deviation, below the mean. Rather, you were 0.25 standard deviations below the mean. The negative tells you you were below. Suppose you had a z-score of 1.1. What was your exam score? Well, that means that 1.1 is your unknown exam score minus 300 over 20. And when you solve that equation, you get an exam score of 322. 322. And finally, if your z-score was -2, that tells you were 2 standard deviations below the mean. So what was your exam score? Well, again, you solve the equation and you get an exam score of 260. So z-scores are useful because it puts everything on the same scale. You have a number, is it big or small compared to the mean? Well, that's kind of hard to say in isolation, but if you know how many standard deviations it was, that tells you a lot. And if you remember from the book, rough rule of thumb, 95% of the data will always be within 2 standard deviations of the mean. So something that's more than 2 standard deviations above or below the mean is going to be pretty extreme data. Something that's half a standard deviation or even 1 standard deviation, not so extreme. Okay, how about this question? On a test, the mean was 400 and Alexandria scored 420. Is she hoping for a large standard deviation for the exam scores or a small one? So she scored above the mean. Does she want the standard deviation to be large or small? Well, if the standard deviation is large, then the scores vary a lot from 400. Maybe some go way higher than 400, some go way lower. And 420, it's above average, but it may not be anything special. But if the standard deviation is small, then the scores are all close to 400, and the 420 makes her stand out. Remember our 95% rule. If the standard deviation was 10, then she would be 2 standard deviations above the mean, which puts her in the top 2.5%. So because she wants all the scores to be close to 400 to make herself stand out, she wants a small standard deviation. The average recovery time for the Nebraskan flu is 13 days, but your doctor says you have a mild case. Do you hope the standard deviation is large or small? Well, you can probably guess. If the standard deviation is large, then some people will recover in much less than 13 days, and because you have a mild case, you expect to be at the low end, so you hope for a large standard deviation. Now let's turn it around. The average score on the SCAT, Standard Coding Aptitude Test, a test I just made up, is 80. When Stephen gets his test back, he finds himself hoping the standard deviation is large. Did he score less than average or above average, above 80? Well, he scored above 80, he would hope for a small standard deviation, as Alexandria did earlier. So he must have scored below 80. He scored below average, but if the scores vary a lot around 80, then whatever his score was might not look as bad. If he scored 75 and the standard deviation was huge, then yeah, he's below average, but not very far below average. Esperanza just had her performance review, which is used to determine her annual bonus. After the review, she finds herself hoping that the standard deviation of the annual bonuses is extremely large. Did the performance review go well or poorly? So she's hoping that when those annual bonuses come out, the standard deviation is really large. So what does that mean? It means she's expecting to be at the high end, and so she must have had a very good performance review. So there it is. You can turn those questions around. And lastly, what I'd like you to do, in our data bank, you'll find a data set called Health 2. And I'd like you to create a statistical portrait of the 4,561 adults in this sample. So use some of our tools that you saw in the chapter 2.1 through 2.4 reading and my earlier screencast. Use some of those tools to create a Word document which paints a picture of these adults. Look at all the variables and ways you can compare them and just try to find an interesting picture. And obviously, you can't do every possible graph or table or summary, numerical summary of the things in that data set, but just try to pick out some that are interesting and give you a chance to use the tools that you learned in the first part of chapter 2. Put them in a Word document and post them on a discussion board, and maybe we'll start class, or at least at some point in class, look at a few of those. That would be great. So go to our data bank. You'll see a data set, an Excel spreadsheet called Health 2. In fact, let me just pull out of here and see if I can find that real quick. Yeah, here's our data bank, and I want Health 2, this one, and I will just move it up so you find it easily. So go into there and try to create a statistical portrait, and I'll put a discussion board form in there where you can post it. Okay, and hopefully next week we'll finally get started in this class. Have a good week.